All right, let's freeze time for a second. We're going to look at the exact millisecond you tap request ride on the Uber app just to uncover the microscopic software battles happening right under the hood. Welcome to this explainer. On the surface, calling a car seems incredibly simple, right? But behind that single tap is a massive, globally distributed architecture working frantically. It's using things like Google S2, spatial geometry, a dispatch engine called Disco, and atomic distributed locks just to solve one of the hardest computer science problems in the world. And it's all just to make sure your ride actually shows up. So, what really goes down in those 3 seconds before a driver is successfully matched to you? To really understand this, we have to look at what would happen if a massive system like Uber didn't have these hidden software protections in place. Without them, the entire system would instantly collapse into a massive concurrency nightmare. And by concurrency nightmare, I mean thousands of computers trying to read and change the exact same piece of data at the exact same millisecond, literally tripping all over each other. Part 1. The double booking race condition. Okay, picture this. Imagine hundreds of people in the exact same neighborhood. Maybe they're leaving a concert or a crowded sports game, and they all request a ride at the exact same millisecond. They all need cars, and the cars are scattered all around them. Now, if the system simply used naive code to find the nearest idle driver, a basic check-then-act pattern, where it looks to see if a driver is available and then instantly assigns them, we would have a massive problem. Because network requests take precious milliseconds to travel, multiple concurrent matching processes running on completely different servers would check the system, see the exact same green car as available, and both act on it simultaneously. It's exactly like two shoppers reaching for the exact same item on a grocery store shelf at the exact same millisecond. Because the software processes both requests at the same time, both riders are told that specific driver is arriving. And the result? One rider gets picked up, while the other is left standing on the curb, getting completely ghosted. The integrity of the whole system is broken. Part 2. Mapping Earth with Google S2. To fix this chaos, the system first has to organize the physical world computationally. It can't just look at a flat map. It needs a way to instantly group people and cars together based on their exact coordinates. So the system uses S2 geometry, which is actually Google's spatial indexing library. S2 effectively projects the spherical Earth into a 2D plane and then recursively divides it into hierarchical, nested cells. You might be wondering, why nested cells? Well, this hierarchical zooming allows the system to adapt to high-density areas, like a packed stadium where it uses tiny square centimeter cells, versus low-density areas, like a rural road where it uses massive square kilometer cells. It perfectly indexes every single driver and rider by their localized cell ID in real time. Part 3. Disco and batch matching. Okay, now that everyone is neatly indexed in these specific geographic cells, the heavy lifting of pairing riders with drivers is handed over to a highly specialized optimization engine that completely rewrites how dispatching works. Enter Disco, the dispatch optimization engine. Instead of panicking and trying to match every request instantly as it comes in, Disco actually pauses. It waits for 2 to 5 seconds to collect all the incoming ride requests and available driver locations in a localized batch. Human behavior is erratic, right? Requests just pour in asynchronously. But by taking a 2-second breath, Disco turns those chaotic, random taps into a highly organized math problem. It acts exactly like a conductor organizing a chaotic taxi stand, surveying the whole board before making a single move. There's a stark contrast here between an old, first-come, first-served, greedy algorithm and Disco's globally optimized batch matching. The greedy algorithm just blindly grabs the closest car, which ends up creating a domino effect of terrible wait times for everyone else. Instead, Disco runs a bipartite matching optimization using mathematical methods like the Hungarian algorithm. This effectively draws invisible lines between all riders and all cars to find a combination that results in the lowest total wait time for the entire group, not just the very first person who clicked. And the results of this are just staggering. By computing the globally optimal pairs for everyone in a specific S2 cell, batch matching slashes the average wait time across the board. In many scenarios, it drops average wait times from 5.5 minutes down to just 3.5 minutes. To put that into perspective, when you multiply saving 2 minutes by 20 million rides a day, the system is effectively saving decades of human waiting time every single week, all because it took a deep breath and optimized the whole grid. Part 4. Atomic distributed locks. So The absolute crucial point here is, once Disco computes all that complex math and finds that perfect optimal pair, how does it actually secure that driver? How does it make sure another batch in a neighboring cell doesn't steal them at the exact same microsecond? It pulls this off using atomic distributed locks. It uses Redis, which is essentially a lightning-fast memory cache, alongside compare and swap queries on custom databases. Now, compare and swap sounds complicated, but it's simply a strict database rule that says, only update this driver's status if no one else has touched it since I last looked. These incredibly fast database operations guarantee that a driver's state is locked down instantly. 15 seconds. The instant an offer is sent to a driver's phone, that driver's ID is locked in the system with a time-to-live countdown of exactly 15 seconds. For that 15-second window, that driver is completely invisible to any other ride request on the network. So if you've ever stared at your phone screen in the pouring rain, wondering why it's taking exactly 10 or 15 seconds to confirm your ride, well, this invisible countdown timer is exactly why. Let's break down the exact life cycle of that offer. First, the system pushes the offer to the driver via persistent WebSockets, which keeps a real-time connection open. Second, the driver is locked in Redis. And third, the driver either accepts the ride, or if that 15-second timer expires without an acceptance, a failsafe rollback instantly kicks in, freeing the driver back up for the next batch. At the deepest persistent database engine level, all of this is protected by that compare and swap logic. A write command only succeeds if the driver's state is exactly strictly ID. If two different regional requests try to claim the same driver simultaneously, the atomic compare and swap ensures only one single transaction succeeds, while it atomically rejects the other. The double booking race condition is completely defeated by pure mathematical precision. Part 5. The asynchronous illusion. While this intense microsecond warfare of distributed locks, batch optimizations, and database roles is raging on the back end, what are you actually experiencing on your phone as you stand on the sidewalk? You just see a smooth, calming, searching animation. And that's because the client-facing booking API is entirely asynchronous. The moment you hit request, the server instantly returns a pending status with a ride ID. If the app wasn't asynchronous, it would literally freeze and crash while waiting for the server to finish all that heavy math. Instead, it masks all of the back-end complexity, giving you immediate visual feedback so you know things are working. Behind that animation, your app simply polls the server, which is really just the software equivalent of repeatedly tapping the server on the shoulder, asking, "Hey, are we there yet?" Or it listens to a WebSocket for updates. So, if a driver declines your ride or if a lock fails, the backend seamlessly resets and pivots to the next best driver from the optimization queue. It does all of this without ever freezing your screen or showing you a panic-inducing error message. It's just a perfect illusion of continuous progress. It really makes you appreciate the crazy engineering involved. Next time you see searching pop up on your screen, will you remember the invisible global optimization engine conquering time and space just for you? It definitely leaves you wondering what other massive, real-time architectures are hiding right beneath the surface of the simple buttons we tap every single day. Thanks for joining this explainer, and we'll catch you next time.